Hello, welcome back to Chapter 13, Section 3, where we're talking about the unit circle, and we've introduced the idea of radian measure. As we start to tell you what radians are, as you go through, like I said, more advanced math and physics, you're going to be using radian measures whenever you're dealing with wheels or things that spin. And there's a lot of things that rotate or spin, for example, the Earth. So there's a lot of physics and math that goes around circles and circular motion. And at first this may not seem true, but it is easier to do the calculations with radians than it is to do it with degrees. And it may not always seem like that, but the key is that whenever you do calculations with radians, all of our radian measures involve pi, or at least they should, okay? They don't have to. You can have just like 1 radian, all right? But if you remember from our unit circle, like all of our radians that go with like, nice numbers with degrees involve pi. Well, we don't have to actually estimate pi all the time. You can even leave that out until the end if I actually even need to estimate it to begin with. So this makes a lot of the math a little bit easier, and this is just one example, all right? So the angle that I have, this inscribed angle in the, using the center of the circle as the vertex of the angle, as the angle increases, this arc increases. Now, I know that if that angle theta is 1 radian, then this r, this radius, equals this distance s. That's how a radian is defined, okay? But if the angle theta increases, all I have to do to find the arc length, if the angle is in radians, is just multiply the angle by the radius. And this gives me my arc length formula. So the length of the arc is just the radius times whatever the angle is in radians. Now this one, I didn't really like this picture because it looks a lot like this picture that I had here at the beginning where it is 1 radian. Maybe it's not. But this is true even if, and I'll try to draw it. It's a bad circle, sorry. So even if I'll make it obvious that it's not 1 radian. If this is r and this is s, this is still true. The arc length is equal to the radius times theta, the measure of the angle. And even if I have an angle of rotation, I'm having a really hard time drawing circles. Even if I have an angle of rotation like this, theta, it's still true. This is s from here to here, and this is r. S is still whatever the radius is times theta. Now, how do we use this? Well, let's try an application problem. All right, so this is basically the beginning of almost a physics problem. All right, if you've never seen this, you gotta go to YouTube and Google this, okay? We have a human centrifuge, and what a human centrifuge does, you can have like a centrifuge in a chemistry lab that spins, and material that is denser separates out by it's like specific density, okay? All right. But a human centrifuge trains astronauts and fighter pilots, and other people have to undergo G-forces. And basically it spins you around really, really fast, and the more you spin, the centripetal force sends you outwards away from the center, pushing you down, and it feels like you're undergoing G's. I've done this once, not with I would have loved to have done one that the Marine Corps uses for their F-18s or NASA uses to train its pilots, but I've actually done this once because at Epcot at Disney World, there's a Mission to Mars ride, and you actually face inward, but it spins, and it spins really, really fast, and you can feel like your weight increasing as you're spinning outwards. Okay, and that wasn't so bad. What was hard for me was the fact that it was like really closed and a little claustrophobic. So you can do the easy one or you can do the hard one, and me and the boys, we actually did the hard one, and it was a little scary. I'll say that. All right, so basically, you know what this is. A human centrifuge is a device used in training astronauts. The passenger cab shown makes 32 complete revolutions in 1 minute. It goes around 32 times in 1 minute, which may not seem like a lot, but it's big, so it's going very, very far. It's going a long distance. We need to figure that out. To the nearest foot, how far does an astronaut in the cab travel in 1 second? So we got to do some conversions here. First of all, I've got the diameter shown as 58. So I need to know, I'm going to be using S equals R times theta. So first of all, I need to know that the R is going to be 58 divided by 2. So my radius is going to be, what is that, 29? 29 feet. Okay, so I need the radius, I got 29 feet. That's good. Now the next thing. I need to be in radians. So the angle that I'm going to travel in 1 second is going to be proportional, because I want to know 1 second, that's what I'm using, but it tells me it makes 32 complete revolutions in 1 minute. So I need to convert from minutes to seconds. So 1 minute is going to be 60 seconds, and the angle in 1 second is going to give me the same proportion as the angle in 1 minute. Well, I need to figure out what the angle is. It says 32 complete revolutions. In radians, a complete revolution would be 2 pi. That's 360 degrees, but we're in radians, so we use 2 pi. So this is going to be 32 feet times 2 pi, and of course this will be radians. All right, so that's my proportion. This angle divided by 1, of course I'm just dividing by 1, so I'm going to get theta is equal to 32 times 2, which is 64 pi divided by 60 seconds. So this is degree revolutions per second, and I can reduce this 64 over 60. Let's see, I think 4 is going to get out. Yep. So I've got, this is going to be 16 pi over 15. Okay, so I know what the radius is. I know what the angle is that I'm going to travel in 1 second. Okay, now I need to put it together to find out what the arc length is going to be. So I've got my arc length is going to be the radius 29 times 16 pi over 15. And in this case, since I do want to get an estimate here, I would just do 29 times 16. Actually, I probably need a calculator for that one. Hit clear. 29 times 16. And I got 464 pi over 15. But since we're actually trying to find to the nearest foot, I'm going to convert that and I'm going to estimate it. So let's do 464 times pi. I'll use my calculator for pi and divide that by, what was it, 15? So it looks like this is going to be approximately 97 feet. It's a little bit more than 97, but to the nearest foot it'd be 97 feet. And 97 feet per second actually might be pretty fast. So that's pretty impressive. All right, we'll see you in the next video.